So now you know that landing slabs are horizontal slabs. So here we will directly calculate the weight. What is our depth? Our depth is 200 mm. So 0.2 into 25 into 1. So it is 5 kilonewton per meter. It is 5 kilonewton per meter. Okay. And then this is the weight of the slab. Similarly, floor finish, which is we assume 1 kilonewton per meter square. It is for running meter per meter. So it is 1 into 1, which is equal to again 1 kilonewton per meter. And then live load we have considered over here 3 kilonewton per meter square. 3 into 1, that is 3 kilonewton per meter. This is the live load. So calculate the total load. So the total load is equal to, it is 5 plus 1, that is 6, plus 3, which is equal to 9 kilonewton per meter. Then calculate factored load or ultimate load, which is equal to 1.5 into 9. So how much it is? So the answer is 13.5 kilonewton per meter. So now we got the load. See, this 17.2 is the total factored load. Okay, this is for west slab. Okay, and for landing, total load is 13.5. Now we got the values of both the loads. Okay, so we will calculate the bending moment now. So to calculate the bending moment, this is your point A. This is the point B. Now we need to find out the total length. So as we know that in dimensions is 6.2 meter. Okay. So landing, we have provided landing of 1.4 meter. After that we have provided steps up to 2.7 meter. You can refer the diagram which we have drawn in the morning. Okay. And near at the approach slab, that stair is there on the ground. So you will get the support reaction at that point in the approach slab, and at the landing slab we have provided the wall. So here this is your reaction RA, here is the reaction RB, and what is the length? So 1.4 plus what is our width of the support? Our width of support is 230 mm. So it is 230 by 2. So 1.4 plus 0.23 by 2. What is the answer? 0.23 by 2 म्हणजे किती येणार? 0.115 plus 1.4. So it is nearly about 1.51. Okay. So this is the point. Here you can see load of landing. What is the intensity of this? It is 13.5 kilonewton per meter. 13.5 kilonewton per meter. And on the remaining, this is your west slab. And here the intensity is 17.2 kilonewton per meter. Now I will mark the distances. First of all, this distance up to this point, it is 1.51 meter. Okay. Now what was our going length? Our single trade is of 0.3 into, we have provided how many trades? We have provided 9 trades, so it is 2.7 is our going length. Okay, and plus width of half of width of support you need to add into that. So 0.23 by 2. So again it is 0.115 plus 2.7, which comes out to be near about 2.81. Okay, so if you mark this distance, this is about 2.81 meter. This is about 2.81 meter. So this is our loading diagram. This is our loading diagram. Now we need to find out the maximum bending moment. So to calculate the maximum bending moment, first we should find out the reactions RA and RB. So we require reaction RA. We are not going to find out the reaction RB, okay, to save our time. So now to calculate the reaction RA, what we will do? We will take sum of the moment of all the forces about B equal to 0. So clockwise forces are positive, anti-clockwise forces are negative. So clockwise forces. Now here this is your point B. Okay. So from point B you need to calculate the distance of all the forces. So first is your RA. What is the distance of RA from point B? It is 2.81 plus 1.51. How much it is? 2.81 plus 1.51. What is the total of these two? So 4.32. 4.32. This is the distance of RA. Then this is moving in clockwise direction. If you see this RA is moving up. Okay, your point is situated over here, B point. So if it is moving up, then it will rotate in this direction. This is the direction of rotation. This is the direction of rotation. So it is clockwise. So this is plus. Then next is this UDL. It is moving in downward direction. UDL is moving in. UDL is moving in downward direction. So if you see this load above point B, it will rotate in this fashion. This is the anti-clockwise direction. So it is minus. Now first, your first job is to convert this UDL into the point load. So it is 17.2 multiplied by 2.81. This is the conversion of point load into the UDL. Okay. Now, sorry, this is the conversion of UDL into the point load. Now this point load will act at the center of the support. Okay. Just wait for 1 minute. This is the distance now. Now this is the conversion of UDL into the point load, and that point load will act at the center. So if I draw over here the point load, this will act over here at the center somewhere here at this point. This will act. Okay. So now from this point you need to calculate the distance. So what is the distance now? This is 1.51. This distance is already 1.51. Now this total is 2.81. So this remaining distance will be 2.81 divided by 2. So how much it is? Calculate the distance. So this much of distance first you need to calculate. How much it is? It is 2.81 by 2. मतलब कितना है? 1.4 some 1.405. Okay, so this is 1.405. Now the total distance, as we are taking the moment about point B. So from point B, what is the total distance? It is 1.405 plus 1.51. 1.51. So it is 2.92. Okay, so the distance is 2.92. This is the distance. Okay. Minus. Again, next UDL you need to consider. So again, this UDL is also moving down, so it is rotating anti-clockwise direction about point B. So first convert this UDL into the point load. So it is multiplied by 1.51 into. Now we need to write the distance. Okay. So first of all, convert the UDL into the point load. So when you convert this, this point load will act at the center of this span. Somewhere here it will act. Okay. And now what is the distance? Now if we want to calculate the distance, then it will be this one. So as this load is at the center, so it will be 1.51 divided by 2. So what is the distance? 0.755. 0.755. So this is the distance. So I will write here 0.755. Then RB is passing through point B, so its moment is 0. So all this is equated to 0. Therefore, after solving this, you will get the value of RA. And let me know the answer. 36.18. Okay, 36.18 kilometer. This is the value of RA. Now, after calculating the value of RA, we need to calculate the maximum bending moment. Okay, so here if you see, the beam is not symmetric beam, although it is simply supported, but if you observe the loading on the beam, the loading is not symmetrical loading. On one side the loading intensity is higher, on another side it is lower, and also the span is different. So you will not get the maximum bending moment at the center. This is the first point. So to calculate the maximum bending moment, first we need to identify the point of zero shear. As we know that to find out the maximum bending moment, at which point the bending moment is maximum, where the shear force is zero. So we need to find out the point where the shear force is zero. At that point, we will get the maximum bending moment. Okay. So here I will write the bending moment. The bending moment is maximum at point of zero shear. Zero shear. Okay. So right now we don't know where is the point of zero shear. Okay, so we will take a general section at a distance x. We will write the shear force equation for that section, and we will equate that to 0, because when we do the shear force 0, then only we will get the maximum bending moment. Okay, so for that purpose now I will erase this, so that in this diagram only we will do the further things. So now here I will take the section now. Suppose now the section line is here. This is our section line. This is our section XX. Now we will calculate the equation of shear force at section XX. So as we have taken section XX at any general distance x. So this section is at a distance x. Okay. This is at any general distance x. So accordingly, you see that this distance is x. This total distance is x. So now shear force at distance xx. I will write the equation. SF at section xx is equal to. Now we can either consider the left hand side equilibrium. This is the left hand side equilibrium, and this is the right hand side equilibrium. As we have taken our value of x from point A, it will be easier for us to go by the left hand side calculation. Okay. So now we will consider the LHS. So when we consider the LHS, we need to we will come across the two forces. First is the reaction RA, and second is this UDL of 17.2 kilonewton per meter. So first is the reaction RA. So now at the left hand side RA is moving upwards, so it is positive plus RA. Instead of writing RA, I will directly write the value of RA. So RA is moving upward. Okay, RA is moving upward, so it is plus. So it is plus 36.18. This is the value of RA. Next is this UDL. So we need to convert this UDL into the point load. It is moving down, so minus, it is 7.2 into x. It is 7.2, sorry, 17.2 into x, where Why I have considered only the length x? Because we are considering the left hand side of this section xx. So we don't know, so we have assumed this length as a x. So it is 17.2 into x. So this is the conversion of UDL into the point load. Still this is the force. We have not multiplied any quantity in the shear force equation by the distance. Okay, perpendicular distance. As we are not calculating the moment, we are calculating the shear force across the section xx. So now this is the equation of the shear force. So I will write here equating shear force at xx to 0. Okay. So therefore SF at section xx is equal to 0, which is equal to, what was the equation? 36.18 minus 17.2x. 36.18 minus 17.2x. Now from this equation find out the value of x and let me know the value. 2.10 because so it is 2.10 meter. So now x is 2.10 meter. From कुठल्या point पासून, from which point? It is from point A because we have measured the x from point A. So I will write here from point A. Okay, from point A. Now we will move back to our diagram. Now we want to calculate the maximum bending moment. Okay, so our maximum bending moment will be at a distance of, what is the distance? 2.10 meters. So I will draw the separate diagram for your better understanding. I will draw half of the diagram only. So this is the line. Here support is there. This is your RA. The value of RA is 36.18 kilonewton. Here is your UDL. 2.81 meter. Here is the UDL, and this UDL is 17.2 kilonewton per meter, and this is 2.10 meter. So we will draw the distance, this point, this total distance, it is 2.10 meter, this point, and at this point we will get the maximum bending moment. Okay, at this point we will get the maximum bending moment. Why the another load is not come into the picture? Now if you observe this diagram, this value of x is 2.10. So from point A, if you go a distance of 2.10 meter, it will be behind this 2.81 meter. So it may be somewhere here you will get that value. Okay, so here. So 2.10 meter. So up to that point, the load is only 17.2 kilonewton. There is no question of taking this 13.5 kilonewton per meter load. Okay, so that is why we have taken it like this. Now calculate the maximum bending moment. So the bending moment, so I will give the name to this point. Suppose that this is point E, this is our point A. So bending moment at point E, which is equal to. So now what is the bending moment? So this is the RA. RA is moving upwards, so its moment is positive. The distance of RA from point E, it is 2.10. This is 13.18 into 2.10. Then this 17.2 kilonewton load, it is moving downward, so minus. So first of all, convert this UDL into the point load. So 17.2 into 2.10. This is the conversion into the point load. So now this load will be act at the center. Okay, this load will act at the center. So the distance from point E we need to calculate, as we want the bending moment at point E. So it will be 2.10 divided by 2, as it is acting at the center. So if you solve this equation, you will get the maximum bending moment. 38.05. Okay. So it is 38.05 kilonewton meter. Okay. So these are the calculations for flight AB and CD. Now similarly, we will do the calculation for flight BC. Okay. So now similarly, we will do the calculation for flight BC. So for flight BC now, I will draw again the diagram. This is your point B. Here it is the point C. Here is the reaction RB. This is the reaction RC. Just 1 minute. Here, what is the length of BC? So now if you observe the BC 1.4 plus 1.8, what was the length for BC? I will here write here randomly. 1.4 plus 1.8 plus 1.4, it was the length. Plus center to center, if you go, it is 0.23 by 2. Here on this side also it is 0.23 by 2. So if you do this calculation, what was the value? Total length? Calculate केली होती ना आपण. Let me know the answer fast. You're taking too much time. Nobody is reacting fast. 4.83 was our total length. Okay, so this is our total length. But if you see now, this is our landing width. Okay, this is our landing width 1.4 meter. So this landing width plus 0.23 by 2. एवढं calculation किती येते? It is near about 1.51. बरोबर ना? So from this point, this is most important things which I am telling to you. हे एक्झाम मध्ये तुम्हाला लोड घेता यायला पाहिजे, कुठून कुठं कुठला लोड घ्यायचा आहे. This point here, up to this point the landing is there. So what was the load on the landing? It is 13.5 kilonewton per meter. Similarly, if you see this portion, okay, so this 1.4 is also landing on this side. Okay, flight BC is having landing on two sides. So 1.4 again it is 1.51. So from this side also at a distance of 1.51. Okay, again here is the load of 13.5 kilonewton per meter. And if you see the middle portion now, this remaining portion, okay, so for this portion there is a flight is there, steps are there, so waste slab is there. So for that waste slab it is 17.2 kilonewton per meter. This is the load. So now what was the actual distances now? So if we write down the distances, then this is the one point, this is the second landing. So now we will write the distances. This distance is 1.51 meter. This is also 1.51 meter. So what was remaining now? How much it is? So it is 1.8 meter. This is 1.8 meter. This is 1.8 meter. Okay. So this is our diagram. Now if you see this diagram, this is the symmetric diagram. Okay. Simply supported beam is there, and if you see the loading, it is perfectly symmetric. So in this case now you will get the maximum bending moment at the center. Why you are getting the maximum bending moment at the center? If you see the support on the both the sides, simple supports are there. On both the sides, if you see, for a certain time, for a certain distance, that is 1.51 meter, same load is there. Here also for 1.51 meter, same load is there, and for the remaining portion also the loading intensity is constant. It is UDF. So loading wise, support wise, okay, it is the symmetrical beam. So if it is symmetrical, then we know that we will get the maximum bending moment at which point? At the center. Suppose now this is our center point. This is our center point. Let us name this point as E. So at the center we will get the maximum bending moment. So if we see the distance, we need to find out this distance. So how much it is? It is 1.51 plus this total is 1.8. Half of 1.8 is 0.9. So how much it is? 1.51 plus 0.9. What is the answer? See, this total is 1.8. So half of 1.8, it is 0.9. So 0.9 plus 1.51, it is 2.41. Okay, so this is 2.41 meter. Here we will get the maximum bending moment. Now to calculate the maximum moment, first we need to know the reaction RB. Okay, so to calculate the reaction RB, what we will do, we will take the moment of all the forces about C equal to 0. Clockwise forces are plus, anti-clockwise forces are minus. This we will do. So now what we will get, so RB into, what is the distance of RB from point C? Distance of RB from point C, it is the total distance. So it is RB into 4.83, it is moving up, so plus minus this UDL, it is 13.5 into, convert this UDL into the point load first, 1.51 into, it will act at the center of, it will act at the center over here. Okay, so from point C, its distance we need to calculate. So what is the distance now? Distance will be 1.51 by 2 plus 1.8 plus 1.51. Get the distance of that. So what is the distance? 1.51 by 2 plus 1.8 plus 1.31. So it near about comes about 4.06. तुम्ही पण चेक करून बघा. 4.06 or 60. I have done it orally. You verify this. Okay. Again minus. Again minus. How much it is? This UDL. So it is 17.2 into 1.8 into, now this UDL is converted into point load, and that point load will act at the center over here. Okay, at the center. So what is the distance? It is 1.51 plus 1.8 by 2. So it is 2.41. Again minus 13.5 into 1.51. This will act at the center, so it will be 1.51 divided by 2, 0.755. I think so. Previously we have calculated, no? Which is equal to 0. If you solve this, you will get the value of RB. Let me know the answer into the chat box. This is 35.79 kilonewton. Now calculate the maximum bending moment at point E. So bending moment at E is equal to. So now we will consider the equilibrium of either left hand side or right hand side. So we will go for left hand side. So now if we go for left hand side, we will see here is the reaction RB is there, a UDL of 13.5 kilonewton per meter is there, and a UDL of 17.2 kilonewton per meter is there, but we need to consider the half of the UDL as our point is at the center. So we are going to consider the length of 0.9 meter only instead of 1.8 meter. So now here from point E, the distance of RB is 2.41. So I will write what is the value of RB? It is 35.79. So 35.79 into 2.41. It is plus as RB is moving upward. It is plus. And this is moving downward. Then it is minus. 13.5 into 1.51 is the conversion of this UDL into the point load, and that will act at the center of this 1.51. So what is the distance from point E? It is 1.51 by 2 plus 0.9. So it is 1.65. त्याच्या आसपास येते बघा. Okay. So it is minus 13.5 into 1.51 into, please cross verify the answers, into 1.65. Okay. Again minus. Now what is remaining? This much of UDL is remaining. This much of UDL is remaining. So how much it is? 17.2 multiplied by this distance. This distance is nothing but it is 1.8 total. So this is 0.9. 17.2 into 0.9 is the conversion of this UDL into the point load, and that point load will act at the center of this 0.9. Okay. So if you write it, then it will be 17.2 into 0.9 into 0.45. This is the bending moment. So therefore bending moment is equal to, so it is 45.55 kilonewton meter. Okay. Now which bending moment is greater? What was our first bending moment? So after calculation of the bending moment, we will take the check for depth. Check for depth. So equating maximum bending moment to moment of resistance. So the previous bending moment was for AB and CD, it is 38 or something, near about 39. This bending moment is 45.55. So we will take this 45.55 into 10 to the power 6, which is equal to MR. So now the grade of steel is Fe415. So for Fe415 it is 0.138 FCK BD square. So here your D is nothing but D required. So therefore 2 is equal to 0.138, FCK is 20, D is 1000 and D required square. Therefore D required is equal to, what is the answer? Mm. So we can nearly round up this depth to 130 mm. And what we have provided, so D required, which is equal to 130 mm, is less than D provided, which is equal to 180 mm. Hence it is safe. This is safe. Okay. So now after taking the check for depth, now do the steel calculations. Okay. So I will write here reinforcement details. You can give any of the heading. You can write here reinforcement details or reinforcement calculations, or you can write steel calculations. I have written here reinforcement calculations. So first we will do it for flights AB and CD. First we will do it for flights A, B and CD. So we know that AST is equal to, what is the formula? 0.5 FCKBD divided by Fy in bracket 1 minus square root 1 minus 4.6 mu upon FCKBD square. So just put the values. Therefore AST is equal to, what are the values now? 0.5 into FCK is 20, into B is 1000, into D what we have provided 180. This whole is divided by Fy is 415 bracket 1 minus square root of 1 minus 4.6 into mu. What was the value of bending moment? 38 point something, no? 38 point. I have written here 05. You check the value and let me know accordingly. FCK is 20, into B is 1000, into D square. So it is 180 square. Okay. See, this type of staircase is there. This is A, B, C and D. So for पहिल्यांदा जे आपण MU काढलो होतो first, it is near about 38.05 kilonewton meter. That was the bending moment. It is for flight AB and flight CD both. Okay, so it is 28.32. So this value is not 38.055. So I am right. So this is C. This is 38.05 kilonewton for these two spans, and for this BC flight, the bending moment is 45.55 kilonewton meter. Okay. Now we are calculating the steel for this one, these two, and after this we will move forward to calculate the steel for this flight. Okay. So here now this is the calculation, and this bending moment, these are for flights AB and CD. Okay, so for that now AST, what was the value of AST when your moment is 38.05? It is 631.79 mm square. It is 631.79 mm square. Check the values, check the calculations. Okay, you should be very careful while doing these calculations. So again check this value. So it is 631.79. So now I will write here, provide, not provide, we have already assumed 10 mm diameter bar. Okay. So here we will calculate number of bars, which is equal to 631.79 divided by pi by 4 into 10 square. So how many number of bars are required? 8.04. 8.04 means nearly equal to 9 numbers. 9 number of bars are required. So calculate the AST provided. AST provided is equal to 9 into pi by 4 into 10 square. So now if you calculate this, you will get the answer. If you calculate this, you will get 706.85. Okay, 706.85 mm square. This is the area of steel which we have provided. Okay, so now we will move forward for the spacing calculation. Spacing of bars. Okay, so spacing of bars, spacing by first criteria, spacing is equal to area of single bar. Okay, what was our standard formula? Area of single bar divided by AST provided is 706.85 multiplied by width is 1000. So you will get the spacing. Okay. So for 2 minutes, just wait, you calculate the spacing. So what is the spacing now? 111. What is the spacing? 111.11. Okay. So 111.11. So we will round up this value to 110 mm. Center to center. Okay. You know that we always reduce the spacing. This is first. Then second, what the IS code says, spacing is equal to, if you are calculating the spacing of main bar, then it is 3D. So 3 into effective depth is 180. So it is 540 mm center to center. And thirdly, it says that IS code, according to IS 456-2000, spacing is equal to how much? It is 300 mm in no case, center to center. Now we need to choose the minimum value of these three. Okay, so minimum value of these three is 110. So I will write here, provide 10 mm bars at the distance of 110 mm center to center for flights AB and CD. This is for AB and CD. Okay. Now we will move to the flight BC. Similarly, we will calculate the area of steel. हाँ, तिथं आले RS portion पाठवायला लागले. So similarly we will do it for flight BC now. So I will give the heading for flight BC. So again, what is the formula for area of steel? AST is equal to, I will write the formula, 0.5 FCKBD divided by Fy in bracket 1 minus under root 1 minus 4.6 mu upon FCKBD square. So now area of steel AST is equal to, if we put the value, then it is 0.5 into FCK is 20 into B is 1000 into D is 180, okay, whole divided by, it is 415 whole divided by, it is 415 in bracket 1 minus under root 1 minus 4.6 into mu. What is the value of mu? Mu is now 45.55 for BC into 10 to the power 6 whole divided by FCK is 20 into B is 1000 into D square is 180 square. Now after solving this, you will get the value of AST. Therefore, area of steel for BC. Now calculate Let me know the answer. 769.49. Okay, 769.49 mm square. So this is the AST. Now again do the same procedure. We have assumed 10 mm bar diameter. So calculate the number of bars. Number of bars is equal to 769.49 divided by 5 by 4 into 10 square. How many number of bars? 9.79. So which we will round up to 10 numbers. 10 number of bars. So now calculate AST provided. AST provided. So we are going to provide 10 bars, each of bar diameter 10 mm. So let me know the answer. 785.39. 785.39 mm square. Okay. So we will move forward for the spacing of bars. Spacing of bars. Now we need to calculate the spacing. So first thing is spacing is equal to area of single bar divided by AST provided multiplied by width, which is equal to, okay, so 100 mm center to center. Second, spacing is equal to 3D, which is equal to 3 into 180, which is equal to 540 mm center to center, and in no case the spacing must be 300 mm center to center. So from above we will provide 100 mm. So here I will write provide 10 mm diameter bars about 100 mm center to center for flight BC. For flight BC. Now this is the main steel. Now we have calculated the main steel of AB, CD, AB and CD, and also for BC. Now next is the distribution steel or minimum steel. Distribution steel. So what is the distribution steel? ASTD is equal to, now torr steel is given, so it is 0.12% of gross cross-sectional area. Okay, so ASTD is equal to, it is 0.12 divided by 100 into B into D, which is equal to 0.12 divided by 100 into the value of B is 1000 and our overall depth is 200. Therefore, the distribution steel ASTD is equal to, what is the answer? 240. It is 240 mm square. So provide 8 mm diameter bars and calculate the number of bars. Here write assume 8 mm diameter bars for distribution steel. Therefore, number of bars is equal to, it is 240 divided by 5 by 4 into 8. It is 4.77, which is nearly equal to 5 numbers. So now calculate the ASTD provided, distribution steel provided. So ASTD provided is equal to 5 bars, each of bar diameter pi by 4 into 8 square. It is 251.32 mm square. 251.32 mm square. So now spacing. Okay. So spacing by first criteria, spacing is equal to area of single bar divided by AST provided multiplied by width. जे आता सांगा spacing लवकर लवकर 200 mm. This is 200 mm center to center. This is 5 into 180, which is 900 mm center to center. And third one is spacing is equal to, it is 450 mm in no case for distribution steel. So from above things we can write provide 8 mm diameter bars about 200 mm center to center, provide 8 mm diameter bars about 200 mm center to center as distribution steel, as distribution steel for flights A, B, C, D and D. Okay, minimum steel will be same for all the flights, because the minimum steel or distribution steel is depends upon the grade of steel. It doesn't depends upon the length of the flights. Okay, so this is the steel design. Now after this, the last thing is the development length. So calculate the development length. LD. It is LD is equal to phi sigma s upon 4 tau BD, which is equal to phi is the bar diameter, maximum bar diameter is 10, sigma s is 0.87 into Fy is 415, full divided by 4 into tau BD is 1.2, and in tension, if the bars are in tension, in tensile zone, we will increase it by 60%, so multiply it by 1.6, then you will get this development length 70.11. So it is nearly about 470.11 mm. म्हणजे कितीला राउंड अप करणार तुम्ही 475 mm. So this is your development length. Now last thing is reinforcement details. So first I will write here for flights A, B and C, D. So now what is your reinforcement detail? For flight A, B and C, D, instead of showing this, we will close this so that we can draw the diagram. Now main reinforcement, main steel. Okay. So the main steel bars will be provided in this. Draw the reinforcement diagram with me. This is your main steel bar. Okay. And the distribution steel is provided, but before drawing the distribution steel, we will provide top extra bars. So now we will draw. One more thing is remaining. These bars are also get anchored over here. So now we will draw the distribution steel. The distribution steel is in this way. Before drawing that, I will complete this profile. Now we will draw the distributions. Okay. Now we will give the name to these bars. So the name to this bar is, what is it is 10 mm 10 mm bar about how much it is main steel. So 100 mm center to center. If any spacing goes wrong, you tell me at that time only. Okay. So now again, here it is this bar. This is the extra bar which 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 is the alternate bar. Okay, and this is the having area 50% of your main steel, main reinforcement. So this bar is also of how much? 10 mm diameter. 10 mm diameter bar about, if this spacing is 100, this will be 200 mm center to center. So area will become half. And then last one is, this is the distribution steel. So this distribution steel is 8 mm bars about, what is the spacing for distribution steel? I forgot. What was the spacing we have calculated? 200. Okay, 200 mm center to center, and this length is nothing but your development length. Okay, this is your LD, development length, what you have calculated. And same diagram you should draw for slide BC. Diagram is same, only there may be the difference in the spacing. Bar diameter is also same. Okay, so these are the flights A, B and CD. In the similar manner, you should draw it for BC. So same profile will be there, same, everything is same. Okay, everything is same, diagram will also same. Just the difference is, here for main steel, spacing for AB and CD is 110 mm. Okay, so I will do the correction over here. So this is not 100 mm. This spacing is 110. This spacing also will get changed if this is 110. So if this is 110 mm, these are the extra bars, which is 220 mm. Okay. So this is the diagram. Now similarly, instead of A, B and CD, you can now you should draw further another diagram for flight CD. Same profile will be there, everything is same. Just you see that here for the main steel 10 mm bars above. What was the spacing for BC? that spacing you should write here. Whatever the spacing you got here, multiply it by 2, and that spacing should be given to these alternate bars. Okay, and this is the distribution still. This will remain same distribution still. Okay, so in this way now we need to draw the diagram. Okay, so with this now we will, our first unit ends over here. Okay, in the next lecture we will start for second unit. We will start for second unit. So right now I will find if I am having some MCQ questions. Okay, now if you finished with the diagram, then you can put your roll number into the chat box. And now you should be fully prepared of this chapter. Anytime your MCQ test will be conducted for this chapter number 1 in upcoming lectures. And from the next lecture, we will start unit number 2. Okay, design of footings.